Okay, good morning, everybody. So last time we talked about some examples of problems involving exponential growth and decay, and we mentioned that we are talking about these applications because exponential growth and decay models are derived from solving one type of differential equations. We call them the separable differential equations. Basically, these are the ones that involves derivatives in which the variables can be separated into the sides of the equation, right? And we have seen earlier that indeed exponential growth and decay models are born out of these separable differential equations. In particular, the equation dp over dt equals k times p, and then we went ahead and looked at one particular example of a separable differential equation. This is number 4 from the worksheet. And we try to solve for the function y that satisfies these differential equations. Recall that a differential equation is an equation that involves the derivative, such as this one, right? You have a y prime on the left-hand side, and we say this differential equation is separable because we can separate the variables, that is, put those with a y on one side of the equation and those with an x on the other side of the equation. And the reason why we want to separate the variables is so that we can get rid of the differentials by taking the integral of both sides of the equation, right? And then the solution to differential equations are not just numbers like what we saw in algebra or pre-calculus. The solution to differential equations are functions, right? And you will note that you are done whenever there are no derivatives nor integrals remaining in your solution. So I guess we talked about this problem last time. I separated the variables, then I integrated both sides, and then after that I come up with this function here, or this relation. And since all derivatives and integrals are done or are gone from my answer here, then I say this is an acceptable final answer. And you see that for this differential equation, there are infinitely many solutions because you can give any number, any value for c, and we still get a solution to the differential equation, right? So this is what we call a general solution to the differential equation, because we are writing all, we are representing all the possible solutions to the differential equation, right? And a particular solution is obtained if you will give a specific value for c. So in some problems, you will be asked for the general solution, but for some, you will be just asked for a particular solution. And when do you know you will get a particular solution? It is when you are given an initial condition, right? Oh, but before I proceed, I see Maria is asking, yeah, we could work on some problems from the written homework. Just send them to me, and then I'll look at the question, and then I'll schedule it. I'll insert it somewhere in our discussion today. Is it a differential equation? Oh, great. Actually, that's a good one, Maria. Yeah, I'll insert that somewhere later. But let's just first look at some examples from the worksheet. Then I'll go to your problem. I always want to start with an easy example first, so that you get the feel of how the process is being implemented. And then after that, let's go to the more challenging ones, like uh, what you sent in the chat. All right. Now, let's try a problem which will ask us for a particular solution. I'm looking at the worksheet number 5, which, by the way, is available on my website, a blank and an annotated version that is. Right? So if you look at problem number 8 in the worksheet, it says that we need to solve y prime equals e to the x minus y all over 1 plus e raised to x, with the initial condition that y of 1 is equal to 0, right? By the way, this is what we call the initial condition, or, well, now I'm hesitating to call it an initial condition because it is the value of y when x is equal to 1. So, well, maybe if you look at the starting point to be x equals 1, then we're fine. So this is an initial or boundary condition. So those that will study differential equations later, you will relearn these terms or encounter these terms again. In the presence of an initial or boundary condition, you are implicitly told to look for a particular solution. So you can interpret this to be y is equal to 0 when x is equal to 1. And you will see later that we will use this info in order to find the arbitrary constant c. So again, we'll redo the steps we did for problem 4 last time, and then just insert a couple of additional steps to find the particular solution. Because again, we need to take care of the initial or the boundary condition. Okay? All right, so let's start the solution here. Again, the first step is to write down y prime in terms of Leibniz notation, because that will make the separation much easier for the variables. So remember that y prime is just another way of writing dy over dx. In this particular case, it would be more convenient to use dy over dx because, again, the first goal is to separate the variables or to check if the variables are separable. Okay, and then here I'll write it as e to the x times e to the negative y all over 1 plus e raised to the x, again in preparation for the separation. And in the numerator, I just employed loss of exponents. So I suggest you look back at that from algebra or pre-cal. And then again, I want all those with those involving the variable x to be on the right-hand side and all those involving the variable y on the other side. So I can multiply both sides by e to the y, so that e to the y will be gone, or e to the negative y will be gone from the right-hand side. And then dy will remain here. And then I have an e to the x over 1 plus e to the x left on the left-hand side. And then remember, I have a dx in the denominator from the left, so I can get rid of that from the left-hand side by multiplying both sides by dx. So essentially, I will get this, all right? And since the left-hand side only involves those with a variable y, the right-hand side only involves those with an x, then indeed we have a separable differential equation. Note that not all differential equations are separable. So if you are a math major or somebody working, or if you are to major in a STEM field, then you will encounter some more complicated types of differential equations. And there are some advanced techniques on how to solve them. But for now, we are only concerned with separable differential equations. And the nice thing about these is that we can simply integrate both sides. Right? And then, the left-hand side is easy. It's just the integral of e to the y dy. So that will just be e to the y. Supposedly, there's an arbitrary constant that comes with the integration. But again, if you remember, our convention is that additional constant can be lumped together into just one constant. I'll put that in the left-hand side. So maybe I'll integrate later, because you notice that the right-hand side will involve a u substitution, right? So for the left-hand side, or the right-hand side, I will let u to be equal to 1 plus e raised to x. Then du would be e to the x dx, which is fine. I can get it from the numerator. So that means the right-hand side is the integral of du over u, okay, which is easier to integrate now. And then I'll integrate now both sides, so I'll get e to the y. Then here I'll have ln of the absolute value of u plus the arbitrary constant c. Again, this constant c takes care of the arbitrary constant coming from the left and the right of the equation. So that's just one big arbitrary constant. And then I'll revert to the original variable x. So I'll have ln of absolute value of 1 plus e to the x plus c. Or you can recognize that 1 plus e raised to x is always positive, so you can drop the absolute value symbol. Right. And then you can leave your answers like this. That's perfectly fine with me, because all integrals and all derivatives are gone. But another way of looking at it is that you can take the natural log of both sides. So you can have ln of e to the y, ln of 1 plus e raised to x plus c, right? And I'm doing this so that I can have an explicit form for y. So this means y is equal to the ln of 1 plus e raised to x plus an arbitrary constant c. My only misgiving about writing y explicitly in terms of x is that here we are putting an assumption that this guy will be positive, because otherwise the natural log will not be defined, right? That's why I usually prefer the final answer to be written in this form. Unless you're told to explicitly solve for y in terms of the variable x, then the first highlighted relation would be fine with me, okay? So this is, these two guys are the general solution, or forms for the general solution of the DE. But remember, we are asked to find a particular solution. So to find a particular solution, we recall the initial or the boundary condition that y of 1 is equal to 0. Again, we interpret it that y will be equal to 0 when x is equal to 1. So we can plug that into either of our two forms. I'll use the first form, right? So again, this means that when x is 1, then y is equal to 0. So I'll just plug in 1 for x and 0 for y. So I'll have e to the 0 equals ln of 1 plus e to the 1 plus the arbitrary constant c, right? And then we'll see that this would be 1 equals ln of 1 plus e plus constant c. And then we can solve for c. C would be 1 minus ln of 1 plus e. Okay? And from this, we get a particular value for c, and hence the term particular solution, because we will not be getting an arbitrary solution with a dangling constant c in the form for our function. So we can say that, therefore, our particular solution is e to the y equals ln of 1 plus e to the x plus the value of c that we got. That's 1 minus ln of 1 plus e. Or, if you want to write it explicitly in terms of y, this would be ln of 1 plus e to the x plus supposedly c for the general solution, but now we know the particular value for c. That's 1 minus ln of 1 plus e. Okay? Is that good? Let me know if you have some questions. Otherwise, I'll go to Maria's question. This is, I guess, from the homework, but the process is still the same. So I won't go much into the details here, hopefully. But let me see. But usually I can't help myself but solve a problem completely and with extreme details. So I hope that if I end up answering this, you try to rewrite the solutions on your own. So try to write it first on your own. If you get stuck, go back to this video and see how it is done. Then try to rewrite the solution again as you submit your homework. Just don't copy what I write. So make sure that you can rewrite the solution on your own. Okay? That will be beneficial for the exam for you guys. Okay? So Maria's question is to find, maybe I should use an asterisk over here. So we need to find the particular solution to the DE, or the differential equation, y squared plus 2y prime equals 3x squared y plus 4y, given y of 0 is equal to 1. Again, even if the problem didn't tell you to find a particular solution, you'll know right away that you're looking for one specific solution because you are given an initial condition over here. Oh, I see, Maria. You just got stuck trying to separate the terms. Okay, that's fine. Let's try to work it out. So or maybe the first part of the solution, then you can continue it. Well, again, always my first step is to write y prime as dy over dx equals, and then I'll try to factor the right-hand side because if you look at the first term here, you have x's and y's mixed together. So what you need to do is to try to factor out one of the variables. And luckily, if you look at the second factor, it also has a y in it. So what you can do is to factor the y and hope that the other factor will not have any y left. Okay, so doing so will give you what? 3x squared plus 4. And now you see that the x's and the y's are separated. Okay, and then now you can do the multiplication and division of both sides to have all y's on one side and all x's on the left-hand side, on the right-hand side. So we'll have y squared plus 2 over y dy equals 3x squared plus 4 times dx, right? And then you're now ready to integrate both sides. But here, if you will integrate this, you cannot do u substitution here, I guess. But since the denominator is just a monomial, you can carry out the division. So, I mean, you can write the left-hand side as y plus 2 over y times dy, right? Just carry out the division first. So y squared over y plus 2 over y equals 3x squared plus 4 dx. And then now you can integrate both sides. And then after integration, you will find your expression for y, or relation involving the variable y, and then use the initial condition in order to get the particular solution. Okay, so is it fine if I leave the rest of the solution to you guys? Do you think you can do it on your own? Okay, again, I'll take your silence as a yes, so I'll leave the rest to you guys. But let me know if you encounter some difficulties in the rest of the solution. Okay. Now, what do you guys want to do next? Do you want to solve another differential equation, or let's move on to improper integrals? I guess for separable differential equations, the intermediate steps are very important. So you need to remember how you do your factoring, how do applying some identities just to separate the variables into either side of the equation. Okay, but otherwise it will just be a straightforward integration. And if you're looking for a particular solution, then you'll just need an additional step in plugging in the y value and the x value coming from that condition to find a particular value for c. Okay. All right. So what do you want to do? What do you want to do next? No opinion. How is your preparation for the exam going? Are you ready for the exam?
Kind of prepared for it.
Yeah, nice to hear that.
Yeah,
Oh, good.
just worried about the graphs and stuff because I feel like they might be in the written portion of it.
Which one? Which one again?
The graphs. Miss Almas
Mm-hmm.
said what it's going to be in there, but I feel like it's probably going to be one of those.
Yeah, usually setting up the integrals that will give you the volume or the surface area for solids of revolution. Those are some of the favorites in the free response part of the test, right? But I actually prefer them being in the free response rather than the multiple choice, because for multiple choice problems, it's all or nothing. If you miss one of the bounds, or if you miss one of the parts of your integrand, then you get 0 for it. But if it's if it's in the free response part, then you might get some partial credits along the way. So yeah. Okay, so it's good to hear that some of you were able to take advantage of the break last week to prepare for the exam, but I understand that that might not be the case for everybody. Yeah, you might have also experienced power or water outages, but yeah, let's see. Okay, let me try just one quick separable differential equation, then we can go to improper integrals. So let's see. Looking at the the worksheet now, and then let me see what would be an interesting problem here. Okay, let's try problem 12. For problem 12 here, we're given the differential equation y prime equals y squared plus 1 all over x y plus y. I guess this is similar to Maria's question earlier, so let's dig into it and let's do this quickly if possible. So again, use Leibniz notation because that will allow us to rewrite the derivative in terms of the differentials dy and dx. So I'll have a y squared plus 1 over here. And then in the bottom, you have x and y's joined together in the first term. So I'll try to factor one of the variables out. Luckily, the second term in the denominator has a y in it, so I can factor out the y. So we'll have an x plus 1 in the bottom times y. And then let's separate the variables. So I'll have y over y squared plus 1 dy equals dx over x plus 1. And then we can integrate both sides. This is exactly the reason why we want to separate the variables so that we can carry out with, we can integrate them. And then if I look at the left-hand side, I will need to let u to be equal to y squared plus 1, the entire denominator. So I'll get the du equals 2y dy. But notice that I only have a dy, a y dy in the integrand. So what I'll do here is to write y dy equals du over 2. So I know exactly that that y dy on the left-hand side will be replaced by du over 2. So the integral on the left would be 1 over u times the du over 2. Okay. And then here on the right-hand side, I can let w to be equal to x plus 1. So dw equals dx. So here I'll have dw over w. And then I'll carry out the integration. So I'll have 1/2 natural log of the absolute value of u equals natural log of w plus the arbitrary constant c, which again takes care also of the arbitrary constant from the left-hand side. And then I'll revert to the original variables. I'll have 1/2 ln of u, but u is y squared plus 1. And I know that y squared plus 1 is always positive, so I can remove the absolute value bars and just replace it with a plain parentheses equals ln of the absolute value of w. But the thing here is that w stands for x plus 1, and x plus 1 can be negative, right? So that means it is important that you leave the absolute value symbol for x plus 1, because x plus 1 can be negative. And remember that natural logs are only defined for positive arguments. Okay, and I guess this would be the preferred form for your solution. Okay, but if you will be required, well, if you will be required to solve for y in terms of x, actually you'll have two functions here, because you'll have a y squared plus 1, then you take the square root, so you get plus or minus the root of something, because essentially I have a y squared here. Even if I get rid of the ln, I'll have a y squared, so I'll have a plus or minus the square root of some complicated function, and I don't want to go there, so I'll leave the answer here. All right, this is a more convenient form for the solution for the differential equation. And it's perfectly fine to stop here because there are no derivatives nor integrals left. Okay, of course, unless you were told to explicitly solve for y. But I see in some of the some of the multiple choice quizzes that you have, sometimes the answers are left in this form and not necessarily in the form y equals something in x, right? Because you will be dealing with more complicated functions if you'll always be required to write the final answer in terms of plainly x. Okay. Okay, yeah, Arsalan, I'm about to start talking about improper integrals, unless you guys have some more questions about separable differential equations. Not? I guess you guys took some time to um, to look at this topic, because if I remember it right, you were just told to watch a video and you didn't have the time to look at it in the lecture or discuss this in the lecture. So I hope these discussions help. All right. So since nobody's reacting, I'm going to go to improper integrals now. Okay. So improper integrals, this is under worksheet 6. Okay. I don't know why, but my note here, when I import this to my notability, my note that this is just lifted from the calculus textbook is gone. So, but these are just from the calculus textbook, so I am not claiming authorship to these exercises. But let's see. Maybe let's have a quick review of improper integrals. So basically, there are two causes of an integral being improper. So if you have an integral from a to b of f of x dx, this is improper if either of the two conditions happen. So if either, number one, if f is discontinuous at some number in the closed interval AB. Okay, so if you look at your integrand f, and then you look at whether it is continuous on the closed interval AB, if it happens that there is a number on the integration interval on which your function f becomes discontinuous, then it's an improper integral. Okay, and the second is that if a or b is infinite. I guess part 2 is the more obvious one, right? So if you see an infinity as one of your bounds, then automatically the integral is improper, right? So the key here is, okay, so if you have an improper integral, you replace the cause of the integral being improper by another variable, and then take the limit of the integral as the variable approaches the number that you replace it with, essentially. So maybe it's better to look at some examples rather than talking it in abstract terms, but that would be the idea. And I'll just want to mention that if you evaluate AB f of x dx can be evaluated, and you get a finite value, then the integral is convergent. So I'll show you later some examples on how to deal with the improper integrals. And then after you do these calculations and it happens that your final answer is a finite number, then you say that the integral is convergent. Otherwise, it is divergent. So there are two possibilities when your improper integral will be divergent. Number one, if the answer is infinity, definitely that's not a finite number, then it's divergent. Or number two, if it doesn't evaluate to any number, to any value at all. Meaning if the limit doesn't exist, you'll see later that evaluating improper integrals involves the computation of a limit. If the limit doesn't exist, then the improper integral is also divergent. So the only case that you have a convergent improper integral is when you get a finite answer. Otherwise, it's divergent. Josh says, is it still improper if the bound itself is discontinuous? I think, Josh, you're referring to if the integrand is discontinuous at one of the bounds. And if that's the case, then yes, the integral is still improper if it is discontinuous at one of the bounds. That's why I put here it's discontinuous on the closed interval AB. So it's possible that the discontinuity happens at one of the bounds, then it's improper. And it's also possible that the discontinuity happens in the interior of the interval. I mean, a number between A and B. So that's also still an improper integral. So hopefully we'll encounter some of these cases and how to solve this. And then I want you guys to pay extra attention to the notation, the notations that I'll be using in writing the solution, because I guess in one of the homeworks or one of the submissions that are due, you were told to observe proper notations. So I guess you will get deductions if you forget some of the notations here. So yeah, pay extra attention to the notations that I'm going to be using. Okay. So let's look at some problems. So I hope you guys had time to browse through worksheet 6. If not, you can take a look at it now and take note of what do you think are challenging ones that we can discuss in the lab. But before that, or while waiting for your suggestions, I'll start with some easy ones just to get it going, to illustrate the process. And then let's go to the more complicated ones later, or probably early on Friday. Okay. Let me start with the exercise, problem number 6. Okay. Problem number 6 is the integral from 2 to 6 of 1 over root of x minus 2 dx. Oh, by the way, the instruction here in worksheet 6 is first determine whether the integral is improper, and if it's improper, state y, and then use proper limit notation and see if it converges. Okay, so let's keep that in mind. So let's see. This is problem number 6. So your integrand is this function, a rational function, or basically a fractional function, and it would be discontinuous if the denominator happens to be 0. So you look at the integration interval 2 to 6. Is there a number on the closed interval 2 to 6 that will make the denominator 0? Unfortunately, yes. When x is equal to 2, which happens to be the lower bound, the integral is the integrand is discontinuous, right? So we say that this is improper because the integrand is discontinuous at x equals 2, right? Which happens to be in a closed interval of integration, right? And then once we identified what caused the integral to become improper, what we can do is change the change that number into a variable, okay, and take the limit as that new variable approaches the original number. So here, the cause of the integral being improper is x equals 2. So I'll rename 2. I'll call it by another name. I'll hide it in the guise of a variable a. 6 is fine. The upper limit is fine because the only point of discontinuity is x equals 2. And then we take the limit of that new integral as the new variable approaches the number 2, right? But we don't want the two-sided limits. We are only after the limit coming from the right. Why do we want the limit from the right? Because remember, the integration interval is from 2 to 6, right? So basically, we are just only concerned over this integral, over this interval. We are integrating over this interval, right? And if we are on this region of interest, the only way we can approach 2 is coming from the right. We don't care whether the limit from the left exists or not, because that is outside the interval of interest, right? So we're only interested on the yellow interval. And on the yellow interval, we only want to know the behavior of the integral as a approaches 2 coming from the right, okay? So that's what we have here. And then now, let's see. Let's evaluate the integral now. Because the lower bound is a, it's not equal to 2 anymore, but it is a number very, very close to 2 from the right, okay? So we can perform integration and apply the fundamental theorem of calculus here. But to do that, I'll need a substitution statement here. I can let u to be equal to x minus 2. So du is equal to dx. So here I'll have limit of du over root of u, okay? But remember that when we are changing the bounds, when we are changing the variable, we also need to change the bounds. So if x is equal to a, then u is equal to a minus 2. So the lower bound now becomes a minus 2, okay? Because again, whenever changing the variable, we also change the bounds, okay? So this is one complication that I don't usually use this way of writing or solving improper integrals. I'll show you an alternative one later for the next problem. But if you want to use the techniques that we learned from previous sections, then this is the way to go. You also change the bounds. So when x is equal to 6, then u is equal to 6 minus 2. So that's going to be 4. Okay. And then we take the limit as a approaches 2 from the right. Let's evaluate the integral. This is u to the negative 1/2. So its integral would be, well, it's u to the minus 1/2. So its integral will be u to the 1/2 all over 1/2, evaluated from a minus 2 to 4. Okay. And then I'll simplify it first as 2 root of u, evaluated from a minus 2 to 4, as a approaches 2 from the right. And then I'll evaluate, I'll plug in the upper bound and then the lower bound. So I'll have 2 times root of 4 minus root of a minus 2. Good. And then I'll evaluate the limit now to remove the value a. So the constant 2 will be here still. Root of 4 is equal to 2. But this guy, what happens to this guy when a approaches 2 coming from the right? Well, the radical function is continuous for any number to the right of 2. So we can simply plug in a equals 2. So we get 0 there. So we get the answer 4. Okay. And you see here the importance of noting that we are taking the limit as a approaches 2 coming from the right. Because if you forgot to write the direction from which you are approaching 2, then the limit won't exist, because the root of a minus 2 doesn't have a limit as a approaches 2 coming from the left, right? But we don't care about a approaching 2 coming from the left, because we are living on the interval 2 to 6. Okay. Now, essentially, what we got here is the value for the integral. So we get that the integral from 2 to 6 of that function over there is equal to 4. And 4 is a finite number, obviously, so we say that this improper integral converges. Oops. It's convergent because we found a finite answer to the limit. Okay? Is that good, guys? Okay, let's see another one. Let me see. Did you find any interesting problem from worksheet 6? If there are still no suggestions, I'll go ahead with problem 23. Integral from...
Questions?
Oh, go ahead.
Okay, the professor did one of the questions in class. I don't know if you have it on your worksheet. I don't have it open, but can you do a question where we would have an improper integral, but in the function there's like a arc10 or something?
Oh, sure, yeah.
Thank you.
Let me briefly look at the choice, the problems here. You want something with an arctan. So probably let's try problem, looking at problem 7. The problem 7 is, well, okay. Anyway, let me do problem 7. Okay. Yeah. I'm thinking about either problem 7 or 8. Problem 7 is more complicated in the sense that it has infinite lower and upper limits. Problem 8 only has an upper limit that is infinite. But I didn't. Okay, let me do 7. Though it's more difficult than what I want to be as my second example. But anyway, you have seen some examples in the class, right? So maybe this will just be a review for you. So I guess it should be fine. Problem 7, integral from negative infinity to infinity of 1 over 1 plus x squared dx. Clearly, this is improper. Since the bounds are infinite. Though take note that it only takes one bound to be infinite for the entire integral to be improper. So if you look at problem 8, which has a lower limit 0 and upper limit infinity, that's still improper, right? So it only takes one bound to be infinite for it to be improper. So if you have here, the cause of the integral being improper is not just one number on the given interval, but actually two numbers. Essentially, in particular, we have the two bounds. So if that's the case, you need to split the integral up into two pieces because the technique that we used, say, in the previous problem, only works when there is only one cause of discontinuity in the integrand, right? Because you replace the variable by another, the number by another variable and take the limit. But if there are more than one cause of discontinuity in the integrand or cause of the integral being improper, you need to split it up into several pieces so that on each of those pieces, you only have one cause of the integral being improper. So in this particular case, I'll rewrite this first as the sum of two integrals. So I'll split it up into two pieces from negative infinity of 1 plus x squared dx. And then since the denominator won't be equal to 0 for any case, I'm free to choose any number here, but I'll just choose 0. But you could pick your favorite number. You can put 17, you can put -7, you can put pi, you can put e. That's perfectly fine because 1 over 1 plus x squared is continuous for any value of x, right? Plus, now I'll have 0 to infinity of 1 over 1 plus x squared dx. Okay? And now, instead of doing the u substitution right away, actually here I don't need u substitution. So I'll first write it as a limit. And this is an important part of the solution, so don't forget it in the exam or in the written homework. You need to write it first in limit notation. Otherwise, you'll lose some points, okay? So here, the cause of the integral being improper for the first integral is the lower limit. So you change it to another name. I'll call it a to 0, same integrand, but take the limit as a approaches negative infinity, plus I'll take the limit of the integral, I'll replace the upper bound by another variable, say b, and take the limit as b approaches positive infinity of the same integrand. Okay. Then we can carry out the integration here. So for the first integral, you still have the limit, but the integral would be arctan of x, but this guy should be evaluated from a to 0, plus limit as b approaches positive infinity of arctan of x, but now evaluated from 0 to b. And then let's write this down out. Let's write this down. So we'll have arctan of 0 minus arctan of a as a approaches minus infinity, plus limit as b approaches positive infinity of arctan of b minus arctan of 0. Okay. Now note, you need to recall evaluating arctans. So arctan of 0 is equal to 0, because basically this is asking us what is the angle whose tangent is equal to 0, right? So basically, remember, tangent is sine over cosine. So basically, we're looking at what is the angle whose sine is equal to 0. Because if sine is 0, then tangent will be 0. And that happens at the angle 0. Okay, so that's why arctan of 0 is 0. And then now, so we know that this would be 0. This will be 0. Okay. And then arctan of a. Well, arctan of a, as a approaches negative infinity, so basically you're evaluating this, right? I'm putting this in quotes because this is technically wrong, because we cannot put an infinity. It's not a number. It's not in the domain of arctan. But essentially, this is what we are thinking. What is the angle whose tangent will give us negative infinity? And remember, this is the angle with tangent of that angle. Let's call that the angle theta equals sine theta over cosine theta. And we want this to be negative infinity, right? So basically, that's a problem. We're looking for the angle theta whose tangent is equal to negative infinity. But recall that tangent is sine over cosine. But how do we get a negative infinity? Well, we get a negative infinity if the denominator is 0, right? And the numerator would be negative 1. So this is how we get negative infinity, right? So basically, we're looking for an angle whose sine is 0 and whose cosine is 1. So if you look at the unit circle, but arctan is restricted here, we will get sine equal to negative 1 and cosine equal to 0 at this angle, right? And this angle is negative pi over 2. So from now on, you can put on your list of things to remember. If you have arctan of negative infinity, sort of, this will give you negative pi over 2. And similarly, you can put in your list arctan of infinity is equal to pi over 2. Because in that case, the angle we're looking for is the angle whose sine is equal to 1 and whose cosine is equal to 0. And that would be pi over 2. Okay, that's when your arctan approach, when the number inside the arctan is is positive infinity. Okay, so with those in mind, so we know that arctan of negative infinity is minus pi over 2, and this guy is pi over 2. So if we simplify, we get what? Hold on, let me just copy this over here. So this would be equal to what? So we have 0 minus pi over 2, so that's pi over 2. Plus, for the second term, we'll have pi over 2 minus 0, so that's pi over 2. So this is equal to pi, okay? So, okay, there we go. So we get a finite number. Pi is a constant, 3.14159265 and so on. So we say that the improper integral is convergent. and its value is equal to pi. Okay. And it is very, actually, this is a very surprising thing, because you're integrating from negative infinity to infinity, so you have an infinite interval, and it looks like the area under the curve 1 plus x squared is just equal to pi. So I forgot what is the graph of 1 plus x squared, but imagine you have something like this that goes into infinity, right? And if you want to get the area of the region bounded there, I'm not sure if this is the graph of 1 plus x squared, but this is a pictorial representation. There are some functions that extends until infinity, and yet they have finite areas. So yeah, that's one interesting thing. Even if the interval is infinite, we get the finite area. And surprisingly, the area is pi. Actually, pi pops up in many applications in math. So it's not just about circles. Pi will just pop up in some interesting equations. So actually, if I'm solving a very complicated problem and in an exam, and I need to guess what is the answer, my candidates are pi, 0, 1, and -1. Those are my candidates if I have to guess. Oh, thank you, Herson. I think I have the right idea about the graph of 1 over 1 plus x squared. Don't you find it very interesting that that will go to infinity, and yet you get a finite area equal to pi? And on top of that, we get a nice number, which is pi. Okay, which reminds me, yeah, it's a usual celebration in the math department, actually all over the world. For math geeks, we celebrate Pi Day on March the 14th. So that would be a couple of weeks from now. So yeah. Okay, so enough of me talking nerd, but yeah, I guess we're out of time for today. So on Friday, we'll talk about some more improper integrals. So browse through worksheet number 6 and see if you want to answer some problems from there, or if you have some problems from the practice test and some of your homeworks, you can also talk about them on Friday. So yeah, have a good day, everybody. See you again on Friday. Good luck on your preparations for the test. Bye.